Okay, so in this video, we're going to examine drawing derivatives on our TI-84. Now, one thing that we should recognize is that we can graph the derivative function, but we can't explicitly define it on our TI-84. So if you're asked to find the derivative, and not just the derivative at a specific point, but the actual function of all the slopes, you can't do that with your calculator. You can check it though, but you can't do it. So let's take a look at how we would graph a particularly strange function. So I'll take my TI-84, and I'm going to graph the derivative, f prime of x, of this function. F of x equals ln sine squared x plus 1. So, take my graphing calculator, and I'll just reset it. It's just easier than clearing everything out and retyping and setting a standard window. And I'm going to go to y equals, and I'm going to type in ln of sine squared. Remember, with trig functions, you have to actually put them in brackets and then square them afterwards. Plus 1. There we go. So I've got the ln of sine squared x plus 1. Now, this isn't the thing I wanted to graph. I actually wanted to graph its derivative. So in my next line, I'm going to go ahead and graph the derivative. So my function is in y1, and I want to graph the derivative of my function. So right in my y equals, I'll type math 8, and I want to graph the derivative with respect to x of y1. Now, how I access y1 is by going alpha trace, and it pulls up my y-vars list. So just repeat that again. I can go alpha trace, and it'll pull up my y-vars, and just hit enter. Alternatively, I could have gone vars, y-vars, function y1, and I would put it in. But I think alpha trace is a heck of a lot easier. Now, I want to graph the derivative at every single possible value of x. So I'll have x equals x. Now, this is going to take some time to draw, so let's start the timer and see what it does. So we can see the graph of the ln of sine squared x plus 1 just creeping along there. You can see it has a lot of different places where it hits 0. Oh, and here we go. We've got the graph of the derivative, and it's negative when that graph is going down, and it's positive when the graph is going up, and negative when the graph is going down, and positive going up. And it's crossing 0 underneath all the maximums and over top of all the minimums. And it's got its own maximums and minimums at all of those points of inflection. And what a beautiful graph of the derivative. Excellent. Now, I can find the point of intersection of these things. The other thing that I can do now is I can trace. So I can trace along my derivative function. I can say, okay, well, what's the derivative at a point where x equals 4? Well, at x equals 4, and I don't know if you can see it on there, the derivative is 0.629062334. So I can use trace once I've got a graph of the derivative. I can also find the intersection point between the derivative and the function itself. So I could go second function calc, and I could choose to intersect. So I'll choose graph 1 as being the blue one, and I'll choose graph 2 as being the red one. And it's asking me for a guess because there's many intersections. So let's just figure out what this closest intersection is. We'll move closer to where we think it occurs. Or we could just type a guess. But we'll hit enter. And it gives us our intersection point. So we know there's an intersection there where the function and the derivative are the same. And that occurs at 4.139 on the x-coordinate and 0.534 on the y-coordinate and on the slope. So that is one way in which we could use graphs of our derivatives. Now, another way is maybe we need to find stationary points. If I need to find stationary points, well, that probably means that I need to find all the places where my derivative equals 0. So I would just simply go second function calc and choose 0. I'll make sure that I'm not dealing with the function itself because y1 is the function. I'll make sure I'm dealing with y2, the derivative. And remember, I have to set left bounds and right bounds. So maybe I'll set a left bound at 0. I'll set a right bound at, let's go 3. And we'll hit enter and it'll find the first one. Well, there is a 0 at 0, 0. So it's going to find that very first solution from left to right. If I set my boundary just slightly to the left of 0 or right of 0, I would have calculated the one that was in between, somewhere between 1 and 1.5. So another thing we might need to do, and I'm just going to go to zoom trig here so that we can see it. So if I go to zoom trig, it's going to make this a little bit easier to see. Maybe not a ton, but a little bit easier. But maybe we need to find times when the derivative is equal to some value of a constant. So it's taking quite a while to graph. But maybe I needed to find the times when the derivative was equal to, I don't know, 1/2. Well, if that were the case, and I'll do my little trick here, it's graphing, it's taking a while, and this happens often with derivatives. I'll press second function off, and that stops the graphing midway, and that allows me to go and add in another component. So I'm going to turn off this graph. If I unhighlight it, it means that it won't draw it. And I'm going to graph a line at y equals -1/2. And that way it'll only graph the derivative and this line y equals -1/2. So we'll now see my derivative starting to show up. It won't take the time to draw that blue graph. And this would be what I would need to do to find times when the derivative is equal to some constant value. Now, since this is taking a while, I'm going to jump to the next thing you might want to do. Maybe you want to check answers. So suppose you were asked to find the derivative of this, or you needed to, and you just wanted to check to see if you were right. Well, we already have a graph of it. Let's go ahead and see if we can figure out what its equation is. So this is a chain rule problem. So the derivative of the outside is ln, so it's 1 over sine squared x plus 1, that's the inside. Now we'll multiply that by the derivative of the inside. Now the inside is also a chain rule problem, so it's sine squared x, so we'll bring the 2 down, that's 2 sine x, and we'll multiply that by the derivative of the inside, which is cosine, and the derivative of 1 is a constant, so it's just going to be that. So I know that the derivative of this is this, or do I? Well, I guess I could check because I have a graph of the derivative. By the way, all those places where it crosses 1/2 are the times when the derivative has a slope, or the function has a slope of 1/2. So that's how we could solve questions like may need to find times when the derivative at some value is equal to some constant. But now let's go and check and see if we've calculated this properly. Well, I'll go back into y equals. I'll get rid of this. I made a mistake there. What do I undo? Oh no. I got to retype the whole thing in. Okay. That was a bad error to make in the middle of filming. Sine x squared. Oh, I did one too many squares. No, I'm good. Plus 1. Okay, and close that bracket off. Good. Okay, I think I've got the function in properly. The one I wanted to get rid of was this 1/2. I'm going to turn the graph of y1 off. So there's the graph of the derivative of y1. Now I'm going to graph this thing that I think the derivative of y1 might be. So I use alpha y equals to pull up fractions. So I could type out my fraction of 1 over, and this is just sine squared. So we'll use brackets, sine x squared plus 1. That's my denominator. I'm going to multiply that by my numerator, which is just 2 cosine, or sine x, cosine x. And we'll check to see if we calculated the derivative correctly. Because if we did, we should see in red the derivative of our function, which is going to take just a little bit of time to draw. And then it should be traced over top of with the color of whatever other color we had in y3. So this is a way to check to see whether or not you've calculated the derivative properly. I actually prefer to check answers to questions that I do this way rather than checking answers in the book or in the back of a textbook, because this gets you additional practice on your calculator. And would you look at that? It's tracing over my graph in black, which means that I have perfectly derived. Hopefully the color change is as clear as it is here. but you can see that that red graph is turning black, and that's because it is now starting to graph the thing that I said the derivative was. And the wheel has stopped, and there is no more red. We have overlapped perfectly, and that is the derivative. So to recap, we can use graphing a derivative to sketch, but we can't explicitly define it. If we wanted to explicitly define it, we got to do this by hand. But we can check to see whether or not we have the correct derivative using our TI-84s. Thank you very much.